Hello everyone, welcome to Civil Engineering and Stuff. And in today's video lecture, we are going to discuss about the relationship between fundamental traffic parameters. So if you have followed the previous lectures in the traffic engineering portion, we have discussed about the fundamental traffic parameters, in which we have discussed that the fundamental traffic parameter can be bifurcated into macroscopic and microscopic. And in macroscopic, we have traffic volume, we have traffic speed, and traffic density as the important fundamental parameters apart from the traffic capacity. So these fundamental parameters of the traffic engineering have certain relationships which are represented in the form of graph, and these graphs are what we call as the fundamental diagrams. And the relationship between these parameters are expressed in the form of fundamental diagrams of traffic flow, which we are going to discuss in this video lecture. All right. So it's of primary importance that at least you should have a basic understanding of like what is traffic volume, what is the traffic speed, and what is traffic density. We have discussed about these in the previous lecture, so just have a basic understanding about these before moving on to this lecture. It's a very important discussion, so you should have a very clear understanding. Okay, so let us discuss the first relationship, and that is speed versus travel time. The first is speed versus travel time, and the graph is shown here, and you can see from the graph it can be deduced that at speed is equal to 0, the time is 0. That is, in the road section there is no vehicle moving, and there is since there is no vehicle moving, there is no speed, and time required to cross this section is also 0. Now, as the vehicles are introduced, as the vehicles are introduced, we can observe that at a very low speed, at a very low speed, the travel time to cross this section of the road is high. That we know, right? This is a very common phenomena that if a vehicle in the study section is traveling at a low speed, it will take more time. If the speed is low, it will take more time to cross this study section. As we move towards the right, that is, as the value of speed increases, we see that the travel time keep on decreasing. You can see here, let's say here if the speed was 10 kilometers, if we move to 20 kilometers, so you can see from here that at 10 kilometer speed, the travel time was this much. Let's say it is, let's say 60 minutes. While at a 20 kilometers per hour speed, the travel time to cross this same study section is around 30 minutes. This is just for example. I'm just telling you in terms of comparison to simplify and compare between the graphs, right? So from here we observe that as the speed increases, the travel time decreases, and as soon as the speed reaches to, let's say, a design speed, after that, if the speed is increasing, there will be a slight reduction in the time, and after that, it will be more or less same, right? It will be more or less same, right? So up to a certain speed level, up to a certain speed level, the travel time will decrease, but after that it will remain constant. Okay, after that it will remain constant. Okay, so the relationship between the speed and travel time is shown in the graph here. Okay, so up to a certain point, let's say the point is O. Up and this is A, B. So uh, till AO, with increase in speed, the travel time decreases, and after O, or at O, section OB, even if the speed increases, the travel time remains same. Okay, so that is the first relationship between speed and travel time. Now let us move to the next parameter, that is speed and density. So from if from the flow diagram shown here, we can see that more or less a linear relationship is observed. This is a simplified version, right? If we plot a graph between the density and speed, if we draw a graph between density and speed, more or less we will get a linear relationship. This uh, may vary depending upon the situation to situation, but the most common form of relationship is a somewhat linear relationship, as can be seen here. Now, from the graph, what deduction can we draw? From the graph, what deduction can we draw? The first deduction can be that if you see at zero density, when the density is zero, when density is zero, we are achieving a free mean speed, and we know what is the traffic density. Traffic density is number of vehicles occupying a section road in 1 kilometer length, right? This means that I will not go into details about these definitions because we have already discussed in the previous lecture. So I highly recommend that you should have a very clear concept what is traffic volume, traffic density, and like traffic speed. It's very important. Okay, so if you haven't gone through the video lectures that have been posted before, just go through it once. That only then you will be able to grab this concept in a perfect way. Okay, so density, as we know, is the number of vehicles occupying this section of road that is taken as 1 kilometer. Now, let's say this is 1 kilometer road section. Okay, our test study area. Okay, this is our 1 kilometer road section, our test study area, and there is no when there is no vehicle occupying, that is all the vehicles are moving. So at that time we are having maximum speed. At that time we are having maximum speed. So when the vehicles are moving, so the density will be zero, and we will have a free mean speed. Right? We will have a free mean speed. That is, no vehicle is occupying the road section. All the vehicles are in motion. We are having a free mean speed. While if you look here at this point, you will see that density is maximum. You will observe that density here is maximum, while your speed is zero. Right? At maximum density, you are getting zero speed. What does this mean? Now this means that vehicles have, like the maximum vehicles have occupied the our study section, and because of that, traffic jam has happened. And when the traffic jam happens, there is no movement of the vehicles on the road section, and because of that, the speed is zero. Right? The speed is zero, which will lead to the maximum density. All right. So if the density is zero, we will get the free mean speed. That is, all the vehicles are in motion. No vehicle is occupying the section of the road, right? And we are getting free flow. And that is what we get, the free mean speed. While at jam density, what is happening on the road? At jam density, the congestion is there. There is no movement of the vehicle. Because of which there is maximum number of vehicles occupying the section of road, and because of no movement, the speed will come out to be zero. Okay, so the common relationship is somewhat a linear relationship. depending upon road to road, like these graphs are obtained through studying the practical traffic flow conditions on the road, right? So after that, these graphs are reduced. So it may happen that graph may be obtained like these. This is another form or in which the relationship between speed and density graph might be obtained. But the most general form is this one, the linear relationship. Alright, so this is the relationship between speed and density. Okay, moving on to the next one, speed and traffic volume. Right, the third relationship is speed and traffic volume. Now let us observe what is happening here. Right, we have traffic volume in x-axis and speed in y-axis. Now let us have a discussion for this. Okay, so if you observe here, if we observe that as the traffic volume is increasing, right, as the traffic volume is increasing, we are also observing increase in speed. As the traffic volume is increasing, we are also observing increase in speed up to this point. Up to this point, let's say this is point O, this is A, this is B, right? From O to A, from O to A, we are observing that with increase in traffic volume, there is increase in traffic speed. Now let us see what is happening in actual road condition. In actual road condition, what is happening is that the number of vehicles are increasing, right? The number of vehicles are increasing on the road, but at the same time, the speed is also increasing, right? Somewhat a free flow condition is being followed, right? We are having the vehicles are increasing, but the capacity of the road is such that that the speed is also increasing up up to point O, right? After point O, what is happening is that traffic volume starts to follow a reverse direction, and traffic volume decreases. But if you observe, the speed keeps on increasing, right? If you like again, let's say this is 0, 10 PCU per hour, let's say 20 PCU per hour, let's say 110 PCU per hour, and let's say this is 200 PCU per hour, just for example, and this is let's say speed of 5, 10, 15, 20, and let's say this is 30, then we have 40, 50, and 60 kilometers per hour. All right. So if you observe here in this section, what is happening is the traffic volume is decreasing. If you observe, the traffic volume is decreasing while the speed is increasing. So in section OB, what is happening is, if we observe here, if we observe on the practical road condition, what is happening? Now the number of vehicles passing the study section is decreasing. The number of vehicles passing the study section is decreasing. And since there is less number of vehicles in the road section, so what will happen? So compared to this OA scenario, now since the number of vehicles are less, so of course the vehicles will have a higher speed, right? When you must have observed in your daily life also, if the road is empty, you go at a comparatively higher speed than what you observe if there is a high amount of traffic or a decent amount of traffic. Your speed is somewhat lower. All right. So this point O is what you get is you can say is the optimum proportion, optimum point at which you will get maximum what? Maximum traffic volume and at a decent design speed, right? This is the point that is giving you the maximum traffic volume at a decent design speed, right? And of course, this B, since being higher, like there is like less traffic volume, so it can be said that it is somewhat a free flow condition, right? It is somewhat a free flow condition or a maximum speed condition. Okay, all right. So I hope this is clear to you. Now, if you observe that for a same traffic volume value, for a same traffic volume value, we can get two different speeds, right? We can get two different speeds. For a same traffic volume value, we can get two different speeds. We have one speed at this point and another speed at this point, right? While the traffic volume value remains the same. So let us understand how and when this can happen. So again, let me just name this as point x1 and this one as point x2. Here we see that at the same traffic volume, we are getting two different speeds. Let us understand how this can happen. If you see here, that is at this section, at a same traffic volume, the speed is less. Okay, the speed is less. When this can happen? This can happen in daytime scenario. This can happen in daytime scenario. That is, let's say from 9 a.m. to or let's say from 7 a.m. to 10 a.m. where at this time everyone is going to their respective workplace, right? Students are going to their school, uh, students are going to their colleges, as well as people are going to their respective offices, right? So at that time, what will happen is the number of vehicles on the road section will increase, right? There will be number of vehicles in the road section will increase, but there is no traffic jam condition. So there is a substantial amount of traffic that is crossing the road section. Traffic volume is the number of vehicles crossing the road section in a unit time, right? So there is a value, let's say 110 in this case. There is 110 vehicles that are crossing the 110 PCUs that are crossing the road section in 1 hour, right? There are 110 vehicles crossing the road section in a 1 hour, and since there are too much vehicles in this road section, so the speed will be fairly less. The speed will be fairly less because there are too much vehicles in the road section. Contrary to that, at point x2, your x2 point can be considered, let's say, a time of 2 a.m. to 5 a.m. Now here what is happening? Here what is happening is, let's say you are doing a 1 hour traffic study just like the previous case we have discussed right now. But here at this time, in your 1 hour, the traffic volume that was crossing was same. 110 vehicles were crossing the road section in 1 hour, but since the road was completely empty at morning time, the road was completely empty. So the velocity or the speed with which the vehicles were crossing was fairly high, right? Since there were not much vehicles on the road, so the velocity with which the vehicles were crossing the road section was fairly high. While contrary to that, though there can be higher amount of vehicles present in the road, but only 110 PCUs were crossing the road section. Only 110 PCUs were crossing the road section, and that is why the that is why at at same traffic volume you can get two different speeds. Okay, so I hope this concept is clear to you. Why or in what scenarios can we get can get two different speeds while having same traffic volume, and what does this graph represent? Right? I hope this is very much clear to you all. Okay, Let us discuss the next parameter, that is relationship between traffic density and traffic volume. And the graph can be seen here. We have a somewhat a parabola shaped graph, and we can see from this graph that as the density is increasing, the traffic volume is increasing to a certain point. Again, let's name this point O. Up till point O, this is, let's say, point A, this is point B. Up till point O, with increase in the traffic density, the traffic volume is also increasing, right? So this section of the graph, what does this section of the graph represent? This section of the graph represents that number of vehicles occupying the section of road, is increasing with, as well as the traffic volume on the road is also increasing, right? This means that number of vehicles occupying the section of the road is increasing. The number of vehicles occupying the section of the road is increasing, while at the same time, the number of vehicles that are crossing the section of road in a unit time is also increasing, right? But then what happens is, after point O, what happens is that the density will increase. If you observe, the density will keep on increasing, but the traffic volume will keep on decreasing. This means, this section means that now what is happening is the occupancy of the vehicles on the road section is higher. The occupancy of the vehicles at the road section is higher, while the movement of the vehicle is lower. Alright, the number of vehicles crossing this road section in the unit time is keep on decreasing, and reach to a point where it becomes zero, where the traffic volume becomes zero. So this point represents the jam density. Alright, I hope I am clear. This part of the road section, what does this indicate? I'll repeat again, that the density is increasing. If you observe, the density is also increasing while the traffic volume is also increasing. The density is increasing. The number of vehicles occupying the road section is increasing, and at the same time, the number of vehicles crossing the road section. And in this scenario, what is happening is vehicles are also crossing the road section. So this is also increasing. But soon enough, after point O, what happens is the occupancy of the vehicles becomes so much that the crossing follows a decremental trend. And soon enough, there are no crossing of the vehicles. All the vehicles are standing still. That is what happens in a traffic jam scenario. The vehicles are now standing still, right? And that is why this point shows the jam density. Alright, this B point shows the jam density. Alright, now if we draw a tangent, from here, let's say this is tangent AP. Okay, this is the tangent AP. So this tangent AP, the slope of this tangent. Let me write here for better visualization. Tangent AP, that is this one, this one. So this tangent AP, the slope of tangent AP, the slope of tangent AP gives us mean free speed. The slope of tangent AP gives us mean free speed. Alright, the slope of tangent AB will give us the mean free speed. Right, the point A, what does it represent? It represents zero flow, zero density. Zero flow and zero density. While your point O refers to the maximum what? Maximum flow or maximum traffic volume. Maximum flow or maximum traffic volume corresponding to the, if you observe here, this corresponds to what? Maximum density. This means that at this density, at this number of occupancy of the vehicles, we will get maximum traffic volume. Alright. So just like in the previous case, if you observe that at same value of traffic volume, I hope this graph, I'll just draw a new graph. Okay, this is density and this is traffic volume, right? So if you observe here, at same traffic volume, let's say it is 500 PCU, we have two different densities, right? We have two different densities, right? Let's say it is just for sake of understanding, 200 vehicles per kilometer, and it is 500 vehicles or 600 vehicles per kilometer. Okay, just for the sake of understanding, this is the point of maximum traffic volume. So we can say at the same traffic volume we can have two densities, or we can say at two different densities we can obtain same traffic volume. But the significance of this is totally different. The significance is totally different. If you see here, we have 200 vehicles that are occupying the road, while 500 vehicles are crossing the road section in a unit time. While here we have 600 vehicles that are occupying the road. The number of vehicles that are occupying are 600, while only 500 are crossing the road. I hope it's clear. I'll again repeat. We have 200 vehicles. We have 200 vehicles that are occupying the road, right? While 500 are moving. That is, the movement of the vehicle are somewhat higher. Right? The movement of the vehicle is somewhat higher. While here the standing vehicle number is higher. We have 600 vehicles that are standing on the road, while only 500 are moving on the road. Right, and because of that, if we follow this part of the graph, we are moving towards what? We are moving towards a jam condition. We are moving towards a traffic jam condition. Okay, so this is one deduction from this graph. All right. So the last topic. So if we want to superimpose these graphs, right? If we want to superimpose these graphs, we have traffic volume and we have traffic speed, and the relationship is somewhat relationship is this, right? We have traffic volume versus traffic density. We have traffic density and traffic volume, right? And then, so the graph is like this. And then we have speed versus density, right? We have speed versus density, and the relationship is somewhat linear. All right. So if we want to superimpose these graphs in one plane, right? If we want to superimpose these graphs in one plane, right? The graph will look like this. The graph will look like this. Okay. This is this is this is what? This is this is this is volume, speed, density surface. Okay, this is volume, speed, density, surface. Okay, these are equal, may not be looking equal right now. Here in this graph, these are equal. Okay, so this is volume, speed, density, surface. If we overlap all these relationships, these traffic volume versus traffic speed, traffic volume versus density, and speed versus density, the overlap relationship volume, speed, density, surface will look something like this. Okay, so this was the fundamental diagrams that showed the relationship between the different fundamental parameters. Okay, so I hope this lecture was useful to you, right? And if so, and if you feel that this lecture serves your purpose, make sure you like the video, subscribe to the channel for more videos like this, and post your views in the comment section. All right. So thank you for watching. Have a nice day.